All right, this is section 4.6, modeling and with exponential and logarithmic functions. And we'll start with the first part. Part 1, solving literal equations for a specified variable. In short, literal equations, you have the definition there, but literal equation means that you have various variables and you're going to solve for one of them, whichever one you're asked to solve for. Let's take a look at example 1. P equals 2L plus 2W, and we're solving for L. So I'm going to subtract 2W. And I will then have P minus 2L W equals 2L, and divide by 2 because I'm solving for L. So I have then L equals P minus 2W all over 2. Okay. Some people want to distribute the division, so you could write this as L equals P over 2 minus W. Either of those will be fine. Alright, so let's go on to number 2. Number 2 is T equals, capital T equals 50 plus 1550e to the minus k lowercase t. Alright, and we're solving for k. So first I'm going to subtract the 50. So I'll have t minus 50 equals 1550e to the minus kt. That's the lowercase t. And so, because I'm going to isolate the exponential, you guys remember doing that? I'm going to divide by 1550 on both sides. So I will have t minus 50, capital T minus 50 over 1550 equals e to the minus kt. All right. And then remember how you're going to solve exponentials. I'm going to stop there on that one, and we'll finish that one in class. Let's go on to part 2, models for exponential growth and decay. So suppose you have f of t equals y sub 0, which some people will say y not, e to the kt. Then if k is greater than 0, then f models exponential growth, so the function is increasing. And if k is less than 0, f models exponential decay. Y not, by the way, will be some positive initial amount or initial quantity. All right, also known as the y-intercept. Let's go on to letter B, some models that work that way. So the first one, a of t, the function a of t equals p to the rt. This models the value of an initial investment p after t years at an interest rate r compounded continuously. So it's the model for continuous compounding. P is the initial amount, r is the interest rate in decimal form, t is the number of years, and a of t is the current amount at whatever time t is. Okay. Number 2, p of t equals p naught e to the kt. Notice it's really the same function, just with different names. Models population growth of an initial population p naught after t years, where k is determined by knowing the population at some point t greater than 0. What that means is we need to know the initial starting population, and then we need to be told after this number of years there are this number of whatever population we're looking at. Okay, and we'll see an example of that. So letter C, creating a model. So the half-life, first, some models that we're going to maybe get to see. One is the half-life, and half-life is the time it takes for initial amount to lose half its value. Doubling time, which works similar, except it's the time it takes for initial amount to double. Number 3, if t and b are real numbers with b greater than 0 and b not equal to 1, then b to the t power is equal to e to the lmb times t, or we can write that as e to the t times lmb. So that just tells us that b to the t can be written e to the some exponent, and this is just telling us how to find that exponent. Number 4, to create a model, given an initial amount and amount at time t, we substitute those values in the function f of t equals y naught e to the kt and find k, and that will give us a model. All right, let's look at the letter D. Some examples. Number 1, an initial investment of 10,000 grows to 14,000 by the end of the 5th year. Assuming continuous compounding, find the interest rate. So, what model are we using? Well, we're using a of t equals p to the rt. I'm going to write that here. A of t equals p times e to the rt. All right, and then I'm going to write what I have. So I have that p is 10,000. That's the initial amount. R I'm looking for, T is 5. And then I also know that after 5 years, that means A of 5 is 14,000. All right, and I'm going to now work with that. So how will I know what the R is? Yeah, well, I have A of 5, which means T equals 5, and I have A of 5 equals 14,000. So I can write my equation or my function A of T equals P to the RT as 14,000. That means the current amount after 5 years, right? Equals 10,000. That's P. E to the R times T, and T is 5. So I could write that as 5R, right? R times 5 or 5R. Okay? I'm going to isolate the exponential, so I'm going to divide by 10,000. So I have 1.4 equals e to the 5R. Yeah? And so because it's an exponential I'm solving for, I'm going to take natural log of both. So I have natural log of 1.4 equals natural log of e to the 5R. Natural log of e to the 5R is, of course, 5R. So I then have 5R equals to ln of 1.4. To solve for R, I divide by 5. And so I get R equals ln of 1.4 divided by 5. And that will be approximately, let's see, 1.4 natural log divided by 5, 0.06 0.0673. I'm going to say 0.067. 0.067. And if you wanted to write 3, and usually we'll know where to round. 0.067, which means 6.7%. Okay, so approximately 6.7%. Okay. All right, and we can test that by using the 0.067 in place of R to see if 10 times e to the 5 times 0.067 gives us 14,000. In fact, let's do that. So we have e to the 5 times 0.067. So I'm going to find 5 times 0.067. Do e to the that times 10,000. Oops. My mistake. All right. So 5.067 times 10,000. E to the. Forgot to do that. I'm going nuts here. All right. 5.06 times 0.067. E to that power, and then times 10,000. And I get 13,979, which is about what it should give me. Okay, notice if I had used 6.73, I think I might have gotten really, really close. All right, let's proceed to part 2. So number 2 is really the same as number 1. Let's read through it, and then I'm gonna just point out some things, and we'll leave this for class. So January 1, 2000, population in Texas was about 21 million. On January 1, 2010, it had grown to 25.2 million. Find a function p of t equals p naught e to the kt. Notice that's the same function we just used, except we didn't call it p, we call it a of t. And we didn't say p naught, we said p for the principal. And we didn't use k, we used r. So p of t equals p naught e to the kt. To represent the population growth t years after January 1, 2000, round k to 5 decimal places. Then find when the population reached or will reach 35 million. Okay, so same example. Notice they're telling us t is the years after January 1, 2000. So on January 1, 2010, t equals 10. So p of 10 is 25.2. Yeah. Initial population is 21. Yeah. The t that you're going to work things with is 10 again, right? Because it's 10 years after the initial population was given to you. And I'm going to stop right there and leave it and just point out that it's like example 1 that we just did, but just using different names for the variables. Let's go on to number 3. The half-life of caffeine is about 5.3 hours. The function C of t equals C naught, or C sub 0, times 1/2 to the t over 5.3 can be used to find the amount of caffeine remaining in the blood after t hours, where C sub 0 is the initial amount. Rewrite the function in the form C of t equals C naught e to the kt. So that was over here somewhere. I think I forgot to read it. No, we did read it. It says if t and b are real numbers with b greater than 0 and b not equal to 1, then b to the t can be written e to the ln b times t, or e to the t ln b. So that tells us that really b is just e to the ln b. And so we replace b with e to the ln b. And so here we just need to know, what is b? Well, if we think of c sub 0 times 1/2 to the t over 5.3, we can think of that 1/2 to the t over 5.3 as 1/2 to the 1 over 5.3, and then all of that to the t power. Okay, so that's our b, is 1/2 to the 1 over 5.3. And so k then, rewrite the function in the form c e to the kt. All right, so that's our b, and so it'll be e to the ln of that t. Yeah, so we just need to find out what is e to the ln of that. Okay, so e to the ln of 1/2 to the 1 over 5.3. Yeah, I'm gonna stop this video there and we'll finish on the next video.